So again, a very warm welcome from me to everyone joining today our digital coffee break. Some of you know me already. My name is Angela and I'm responsible for marketing here at AppWorks. And just again, another ramp up on who AppWorks is. So we are a 100% subsidiary of Premium Aerotech and part of the Airbus family. We design, develop and manufacture 3D printed parts. And before handing over to our speaker of today, which is Phil Parks, just a few technical remarks. So you can see, as for the last time, a Q&A session below. So whenever during the presentation some questions arise, which I hope, and just add them in, and after Phil's presentation, we will go through the questions and try to answer all of them. Yeah, so as always, it's time to grab your coffee, lean back and listen today to Phil Parks, who is our technical lead for the Hyperjoint and the head of virtual product engineering at AppWorks. So have fun and enjoy.
Okay, thank you very much for the introduction. Yeah, so I'm Phil Parks, so software engineer and design engineer at AppWorks. And my background is in R&D, development at Airbus, working on hybrid structures and research on additive manufacturing. As Angela said, we're a wholly owned subsidiary of Premium Aerotech and part of the Airbus family. And this is quite a key thing for today's talk, because this really gives us access to a really wide and diverse range of technologies. And it's really our mission is to take these and apply them in new markets. So like aerospace, automotive, motorsport, sailing as well. So apply to new markets outside of aerospace. And we've got a couple of examples here, and you may have seen the previous coffee break sessions on Scalmalloy or 3D surfing. And these are examples, again, of technologies that have come from Airbus research programs and are now being made available to new industries and much more widely via ourselves at AppWorks. So today we're focusing on the Hyperjoint, so the element you see on the right-hand side. I know we have already had a brief introduction in our first coffee break session to this topic, but today we'll be going into a little bit more detail. And particularly a difference is that we'll be looking at some case studies as well as how we've applied the technology in the past in some of the demonstrators that we are able to share with you, and really show you what's possible, and hope that this generates some ideas of how we could help to support you to apply it in your own business. So here's an example. So we have a titanium fitting, additively manufactured with arrow-headed pins embedded into a composite sandwich structure here. So hybrid penetrative reinforcement really allows us to create very lightweight, high performance and damage tolerant metal composite structures. So, and this is really achieved by the profile of the pins that you can see on the right hand side there. So around about 1 millimeter in diameter, 2 or 3 millimeters in height. And you can think of it as metallic Z pinning, but the key difference is that the head feature that we can create and the freedom we have to control the profile and the geometry of the pins. And what this gives us is a mechanical interlock between with the composite fibers. So it's not just bonding. We have bonding as well as due to the epoxy, for example, that's within the composite matrix. But it's this mechanical interlock that really gives the performance that I'll show you in some of the later slides. Another key factor compared to some other technologies is that if you're 3D printing your component, then these pins kind of come for free. You get your joint for free because there's very little volume of material in these pins because they're so small. And this really is my next point, that the workflow is very streamlined. So the joint can be created with the main part, bracket, for example. And then when it comes to the integration and the assembly, this is streamlined because we've got no mechanical fastening processes such as drilling and shimming. Now, as I already said, this is a technology that's come from Airbus, but is being developed, further developed and delivered by ourselves at AppWorks. So very quickly, so how we actually go about integrating these joints. The key thing is that it's easy, regardless of what your existing composite workflow is, we can integrate this technology. So on the first step, on the left side, we prepare the bracket. So we print the bracket and do all the necessary post-processing steps and machining, and also prepare our composite stack. Now this can be a dry fiber for a resin infusion process, or it can be pre-preg if you're using an autoclave process. We can accommodate either of these approaches. So it's really very versatile and, as I've said, easy to integrate into your existing workflow. So once everything is prepared, we position the part using some tooling to locate it and then integrate. So this is, again, just to reiterate, whilst the composite is still in the green state, and the integration is done using a combination of heat and pressure and ultrasonic vibration sometimes as well. So just to help the pins in between the fibers. And then finally, step 4, either infuse or go into the autoclave. Now, another approach you can see on the bottom, it's kind of the inverse of the first approach, where the bracket itself is kind of sitting in a pocket in the tooling, and then the composite material is applied on top. So again, it's quite flexible in terms of we have various approaches that we can use. So what is so great about the Hyperjoint? And really, it's the best of both worlds, in my opinion, between some of the strengths of bonding and some of the qualities of bolting as well. So if we start with bolting, yeah, it is undoubtedly a good option if you've got very high loads and as a result, thick composite materials. So let's just generalize, say around 10 millimeters or more. And compared to a bonded joint, bolts give you high residual strength after initial initiation of failure. However, if you've got a very thin composite structure, then these bolts really are a weight penalty and are adding additional steps to your assembly process. So by contrast, bonding is great if you've got thin structures, so maybe 2-3 millimeters, and it's very lightweight and it's very stiff. However, the big downside is you don't have any residual strength after the initiation of damage, and you're likely to get catastrophic separation of the joint. And again, we've got a lengthy assembly process because of the sensitivity to surface preparation and cleaning. So hyperjoining, we have high residual strength after the initiation of damage, highly damage tolerant, lightweight and stiff. So it's really the strength without the weight. So this is the best of both worlds. And it's really bridges the gap. You can see it's competitive for maybe 2.5-3 millimeters up to 10. So it's really filling this middle ground between when you might use bonding or when you might use bolting. By additive manufacturing is the enabling technology, and as a result, in combination, we have new design possibilities as well, and the streamlined workflow I've already described. So quickly, just to look at some of the performance of the joints, because this was included in previous coffee break session. So generally speaking, we have around 6.5 times the strength of a traditional simple adhesive joint. Now, the interesting thing here, you can see that there are 2 dark gray lines, and the left-hand one, where we have no bonding, is when we've artificially inhibited bonding by using a release agent. So this is quite a conservative approach, and but as a result, you can see there's very low scatter as well, because there isn't the inconsistency in the bond line. So this actually gives a really nice design allowable design value to use for design. And as I say, it is conservative and it's reliable. There is a small increase when we do have the bonding, but you can see that the scatter is slightly increased as well. So if we look at force versus displacement for the same 3 data sets, you can see that the energy absorption capability that we have, and due to the increased extension at maximal load, compared to the lighter green is when we have no bonding, so still a very significant increase compared to our baseline, which is a pure bonded joint in the pink and the red at the bottom. So I should have said that this is for lap shear testing, single lap shear, as you can see on the left side. Now, coming from an aerospace research environment, we did huge amount of testing, and we have a huge amount of test data to fall back on. And we really spent a long time characterizing the design envelope. And here you can see for a static case versus a bolted joint, an equivalent bolted joint. So on the vertical axis, a tensile loading, so that's a pull-out condition, and on the horizontal axis, shear loading. And you can see that the joint does perform slightly better in shear than in tension. But the crosses you see are firstly for bolt damage initiation and then for bolt failure. And you can see that even if we use the minimum failure load, so again, add another level of conservatism, the design envelope far exceeds the values for the bolted joint. Now, a lot of people ask, okay, pushing these pins into the composite material, what are you doing to the strength of the composite structure? And yes, we are causing a small amount of fiber misalignment when we push these in. The key thing is we still retain the material. We're locally changing the fiber volume fraction, but this we still have a continuous load path. So unlike a bolted joint when we're drilling a great big hole and breaking the load path, and you can see here, so for a field hole tension test, or basically the specimen you see here loaded in tension, the bolt, you only have around half of the original strength of the composite material, whereas the Hyperjoint, you only lose about 20%. There's a slightly less of a difference for compression, but the Hyperjoint still performs better. So in summary, you see on the right-hand side that a Hyperjoint is less detrimental to the composite structure, the underlying structure. So focusing now a little more on motorsport applications as one example of, in short, you can see a huge amount of opportunities and a huge range of different ways in which this technology could be applied in this setting. And the main graphic is the race car you see here, but also it would be equally applicable to high-performance sports bikes as well. And so just some examples of how we could use the joints, or so to interface with your monocoque, with the body or the chassis, or smaller structural elements, the attachment of smaller structural elements, like some of the aero features you see on the car here, diffusers. But we should also think about not just the primary structural elements, but we've actually seen some really interesting cases recently of how we can apply this actually within electrical systems, electric motors, so electromechanical systems and drive shafts and couplings between composite tubes, for instance, and flanges, this type of idea. But also something I'll show in one of the later slides is also systems installations. So hyper-jointed fitting studs that actually allow very rapid equipping of your wiring harnesses or hydraulic lines and this type of idea. So we'll look at those in some more detail in a moment. But what I want to do, as I've already said, is today show some case studies of how we've applied this technology in the past in some demonstration cases, and to really show you what's possible. And I hope that this will allow you to generate some ideas of how it could be used in your own business and your own products to improve performance, improve damage tolerance, streamline your workflow, or maybe also for you to identify some challenges you may currently be having in assembly or integration where we might be able to support you to remove these pain points. So the first thing we'll look at is this bike seat. I mean, you may have seen this on the internet before. It is something we did quite a while ago. However, it's a great example of how we can generate an ultra lightweight solution and use this technology for very thin composites, so 1.5 to 2 millimeters thick. So literally just a few plies. And another key feature of this particular part is that the interface surfaces have double curvature. So, we're not just constrained to flat panels. Double curvature is not a problem. And, we wanted to see how far we could really push this idea. And you can see the example on the right where we can use this hyper-joining to reinforce a corner structure like this on really quite a tight radius. So this is maybe around a 20 millimeter radius. Now, if we think about the synergies with motorsport, maybe some of the aero features we showed before, I could imagine that the composite is very thin, and therefore we want a really high damage tolerant, lightweight and stiff solution, and that's something that we can offer. So if you see the Venn diagram in the top right, this is really looking at how Hyper is enhancing what would otherwise be a bonded solution. Now, if we look at a different type of fitting, this is actually where we've replacing a bolted solution because the loads are much higher. And the key thing about this is that we have no fastener penetration. This was particularly because the pins are only about 75% of the thickness of the composite. And this was particularly important in this case because it was an aerodynamic panel exposed to the airflow. And again, it has double curvature. And you can see the number of pins there is quite high, about 140 pins, because of the increased loading. And more pins, it is a little more tricky to actually insert because you need a greater force. But going through this exercise, we developed some innovative solutions of how we can actually integrate a part like this, which is a very organic topology. So you've not got a lot of flat surfaces for the integration process, or for that also creates some challenges when we come to bagging the parts and the tooling for the cure as well. But as I say, through this process, we now have solutions to these challenges. And another thing that's not initially obvious looking at the photo on the left is that this part is completely hollow. So it's a very lightweight solution. You can see this in the section on the right-hand side. And one really interesting and nice feature about this part is we introduced this very thin skin. Now that's almost like a cool plate. So it's flying tooling because otherwise this cavity would completely fill with resin. So again, this is another example of some of the innovative design work we've done on this technology and how we can, as I say, generate something that's very lightweight and hollow, but still fit for the process of infusion or going into the autoclave. So again, the freedom of using additive manufacturing for the creation of this joint really allows us to combine different methodologies and different solutions, different approaches within one component. So you can see here on the left side, we have a hyperjointed interface on the lower surface of this bracket, but then we have a gyroid structure on the upper side. And these components were produced by initially pushing the hyperjoint into the fairly flat bottom part of the composite structure, but then using short fiber injection to actually create this rib structure. And this approach, which was developed with our parent company, with Premium Aerotech, really allows a much higher volume production. So coming back to motorsport, maybe this is something we could actually see for not necessarily mass production automotive, but however, sort of low to medium batch racing applications, or also supercar, hypercar type applications for door panels, bonnets, wings, and so on. Because not only are these very high performing structures, so stiff, damage tolerant, as I've said before, but we also have the ability to create quite aesthetically pleasing parts as well, that may be on show in some of these applications. And the final thing that I already touched on a little bit was that we can actually combine a mechanical fastening with the hyperjoint. Or, as I say, one example would be the installation of systems components, and really it allows rapid equipping of hydraulic lines or subcomponents, subsystems on, say, a main monocoque body or chassis right out of cure. So you would, as I say, have a large monolithic composite part, and you can imagine it comes out of the resin infusion process or it comes out of the autoclave, and you've got all of these studs in all your correct places all over the fitting, ready for your next step. And as I say, your assembly process is really, the time is reduced significantly. Okay, so as I said, hopefully this has sort of shown you what is possible. Some ways we've implemented the technology before, how it could be applicable in your own business or could help you with certain pain points that you have. And hopefully that's the case, and hopefully this has been interesting. So what's the next step? Now, following this webinar, if we don't already have an NDA with you, it'd be very quick to get that set up, and then we can discuss your applications in more depth and more detail, and specifically look at the components that, and I help you to identify components as well, where we could apply as technology. And this is just an example project structure that we've used for other customers in the past. So once we do have a potential candidate part or application, you know, what we've done in the past is to do a feasibility study and really look and analyze the problem, look in more depth. You know, will this work? And then have a gate review before going into sort of the main part of the project, where we would actually redesign, topology optimize, do the design for manufacturing, additive manufacturing, design for integration, and design for cure. Then, say a second stage, a second work package would be to actually do the manufacturing, because at AppWorks, we really offer end-to-end solutions. So not just the design and optimization work and the engineering, but then it's the production as well. Now we can, for sort of stage 3, where we actually come to integrate the structure, we can either work with our own composite partners that we have, or if you're doing that in-house, or you have your own trusted composite partner in your supply chain. As I say, we're very open to collaborating and finding a solution that works for your particular setup. So I hope I've been able to show you what's possible, how we've applied it in the past, and as I say, helps you to generate some ideas of how we can potentially support you to introduce this technology into your own business, and maybe remove some pain points when it comes to assembly and integration, and also to improve performance of existing components as well. As I say, reducing weight, increasing stiffness and damage tolerance. So thank you very much for your time. And yeah, I welcome any questions you may have.
Thanks, Phil. And we will see whether everyone still has some open questions which arise. So whenever there are some, please add them. And Phil is still here to answer them. But I think you also had some other intensive topics, Phil, right? Which
yes, yeah. So yes, we have one question here asking around, you know, what is it just? So I showed quite a lot of data on static testing, but no, this is by no means all we've done. As I say, we've really spent a lot of time doing a huge amount of experimental data capture and testing on fatigue performance as well, lightning strike, compression after impact, impact damage. So as I say, particularly in a motorsport environment, that might be of interest to the audience, that we, in summary, like the damage, if you get an impact in the region of the pins, the propagation of damage is much less than if you have a bolted joint or no feature at all. So it really helps to minimize the propagation of damage. Okay, so we have a question around the surface roughness. So what we actually have developed, in one of my first slides, I showed you that another sort of technology that we have access to is 3D surfing. And you can imagine if you use electrochemical polishing on these small pins, that you would, they would be eroded and you'd be left with nothing. However, we've actually developed a methodology that allows us to apply 3D surfing to these pins and still retain the profile that we want, the nominal profile. So yeah, surface roughness certainly would be a factor if you weren't applying some sort of post-process treatment. But as I say, we have a solution for that, which really helps with the fatigue performance. Because yeah, the fatigue performance on the pins in like an as-built condition clearly wouldn't be too good. So in terms of what surface roughnesses we're able to achieve, one of the other questions there, I'd actually sort of refer you to my colleague Max's presentation specifically on 3D surfing that was a couple of weeks ago. Am I right, Angela, that that's actually available on YouTube now?
Yeah.
So I would, you know, he would be able to give, or did in fact give a lot of detail on what we were able to actually achieve with 3D surfing. But it's the RA and RZ is very low. That is the short answer. So one more question here in terms of methods and tools for actually modeling of the joints. Yeah, so in addition or in parallel, whilst we were doing this extensive experimental testing a few years ago at Airbus, we were, in parallel developing the modeling methodologies. And yeah, we have a whole range. So from simple, you know, beam spring models that are suitable for initial sizing, right up to explicit finite element models as well. So we have a real range depending on the need.
Phil, also on this question, like which I think you also already answered partly, it was also asked with which values we recommend for these surface roughness, if I get that right.
Well, actually, I think the question here is actually referring to the roughness of the surface, the interface surface which the pins are on. And yeah, I'd say that maybe a small amount of roughness on this surface. You certainly wouldn't want it to be in the as-built condition, but a small amount of roughness on this interface could actually help to enhance the bond strength. But as I say, what we're primarily focusing on, or we're designed to, is really the mechanical interlock that's offered by the pins. And therefore, my primary focus would be to really ensure that the surface roughness on the pins themselves, because that is really what's doing the work, is as low as possible. And then, as I say, if it was, it would only be better on that. So if we were, for example, applying 3D surfing to improve the surface roughness of the pins, it would only be better on the main interface surface.
Okay.
And yeah, so the next question is, yes, have we added the pins to a non-additively manufactured part? Yeah, and this was actually something we did, you know, right back in the sort of the early development phases, several years ago, because at that time, additive manufacturing was still quite costly and slow. So really, how could we get the most value added from the technology was to mill a part and then put the pins on top. And this is certainly possible. As I say, I think the best benefit from the technology really comes from, you know, really taking a high level view and saying, okay, I'm going to redesign the part for additive manufacturing. I'm going to get all of the benefits and weight reduction from topology optimizing the part. And then I'm also going to incorporate Hyperjoint. And this is really, as I say, from thinking from the ground up rather than trying to take something that's maybe a milled part and currently bolted and just trying to put pins on it. You know, sure, that would work, and we can do it. Is the short answer. We can do it. But it really, those first few layers that you put down, well, firstly, if you are putting the pins onto an existing part using powder bed, using a powder bed printing technology, then it's got to be completely flat, or you can't recoat powder over the top. And so that's the first constraint in that approach. And yeah, it's really critical to get those first few layers to really sinter them well so that you get a good interface between the additive part and the milled part. So for me, yeah, it can be done, but it is a little bit challenging and does apply some additional constraints that aren't there if you are producing the part additively anyway. And
so you still get time for those 2 questions, Phil.
Okay, so yes, so we are using an erosive technology to improve the surface of the pins. And yes, certainly that is an element that the question is asking, do we add additional volume to the pins, basically an offset to prevent erosion? And that is certainly part of the approach. It is a little bit more complex than that to ensure that you really get the profile you want. But yeah, that is in essence part of the process, yes. And in terms of cost benefit and life comparisons of components using this technology, I'm not sure we could really discuss that too much now because, as I say, we are limited in what we're able to share in terms of demonstrations and real components because of confidentiality. So I'm not sure I could say too much on that, I'm sorry. But as I say, if you had something particular in mind, we could do more of a deep dive on that and look into that on a case-by-case basis. So I think as we're almost out of time, I'd say I'd really ask you that if hopefully this has been interesting, and if it has and you see potential within your own business, then really to reach out to us and get in touch. And as I say, we can then have a look on more of an individual case-by-case basis and more of a deep dive and get into the analysis of whether it could work for you.
Cool. Yeah, thanks. Thanks, Phil, for all the good insights and for answering all the questions. That was really good introduction and a really good topic. Yeah, and a special thank you from me to everyone who joined, and especially to everyone who joined the whole series. As you see on the picture here, there is no picture for the next coffee break, as currently this series it stops, and I really hope that we could bring some content, like transfer content to all of you during those, let's say, really special parts. That's why I replaced the picture with the heart, which is just saying a big thank you to everyone. Big thank you to Phil today, and a big thank you to all of you who were a really good audience and who brought a lot of questions and a lot of interaction, which really helped us. Yeah, so whenever you want to stay connected with us, as it says here on the slide, connect with us on social media. We are also meanwhile on Instagram, and there you can see our motorsports work and all our motorsports efforts and projects we're working on. And yeah, as the interest was quite high on this coffee break, I think we will find another way to connect with you and maybe go for a second series if people are interested. Yeah, so thank you to all of you. Have a good afternoon. And yeah, I hope to see you all soon, maybe live or again in a digital coffee break.
Thank you, everyone. Thank you for your time.
See you guys. Bye-bye.